Hello, everybody. I'd like to introduce you to your hosts, Dave Carter and Tom Smith.
Thanks, Angie. Like Angie said, I'm David Carter. I'm STEM Training Director for Vernier. I've been using Vernier probes. This is going on year 31 for me. It's been a long time. I used to run the instructional physics labs at the University of Mississippi a long time ago. And then I taught middle school and have done lots of PD workshops over the years. And I'm based in our Tennessee office. I am the Tennessee office. But anyway, that's who I am. And then we have Tom.
Hi, Tom Smith here from the Beaverton office, the world headquarters of Vernier Software and Technology. And I've been with Vernier for about 6 years. Before that, taught physics and engineering at the high school level. So I have about half as much experience as Dave does working with Vernier equipment. Looking forward to today's webinar and hope you are too.
Well, I'll go ahead and start my part of the presentation. What we want to do, of course, today's topic is work and energy. We've been trying to do topics that fall into maybe where you are in the curriculum. And so we're going to be showing a couple of labs that are part of our remote resources. And I want to show you where they came from. We put up these files for you, just 2 of them, but this is just 2 of many. There's over 300 different labs that are available that you can download for free and be able to have data to analyze. And so I want to show you where that comes from. So I'm just going to start off by showing you really quickly our website here. And so let me go here, and I just wanted to share that. So what you're seeing now is our homepage. And on the very top there, or there right there in the middle, it says Explore Remote Solutions. And so I'm going to go that route. And when you get here, they have it kind of divided up as K-8, high school, college. Some of it leads you kind of down the same path. I'm just going to go down the middle path there, the high school path. And there are several things that are available for these times that could be useful to you. We did a webinar about just about these resources earlier in the year, so you can check that out. Vernier Graphical Analysis Pro, that may be something you're familiar with if you're doing physics. We may get a little chance to talk about that at the end, but it's a program that allows you to use videos to analyze motion. And Tom may talk about that towards the end. It's a 30-day free trial, so you should check that out. The Pivot Interactive has been a lot of interest in that, and then the other free stuff. And I'm going to go right down here to the experiment library, because this is where the labs came from. And so I'm going to go here to View Library. And so these are labs from our various lab books. And if I browse the library, you'll see what's available here. So when I open this up, it actually defaulted to what's in the biological sciences. Let me go to physics, since we're doing a physics workshop here. And what you're seeing is a variety of labs from the different books. So this would be from our advanced physics book. So there's the lab, there's the software that's used with produces the lab. And the idea is that you can go here and pick a lab that you want to do. So you have the data that you can analyze, and it's got the software there. So like motion, that's what we've chosen here. But this is where they came from. So if you clicked on that, it's the same links that you were sent there in the chat window and in emails. But that's where it comes from. And I won't actually go down that path, but I just wanted to let you know that this is where it is, and that there are more options here. And a lot of them are for Graphical Analysis 4 because it's a free software. And so it was easy. Chromebooks, computers, iPads, Android phones, and all of those. So it's widely available there. So that's where this all comes from there. So what I want to do there is I'm going to stop sharing that screen. And I'm going to be doing the ball toss lab. And what I'm going to be doing is I'm going to be using graphical analysis, but I'm using Graphical Analysis Pro. This is a new version that has new features. And the feature I'm going to highlight in my presentation will be the data sharing option. And data sharing allows me to collect data on my machine. And if you wanted to, and if you have Graphical Analysis Pro, if you've gone through the little tabs to be able to do that, you could receive the data also. Now, I'm going to demonstrate it by collecting data on the computer, and then you'll see it on my cell phone simultaneously. And I'm going to be doing, just to get a little data here, I'm going to be doing the ball toss. And so I'm going to be using the motion detector. So this one has been around for a long time. So the motion detector uses ultrasound, sends out a pulse of sound, it bounces off the object and measures how far away it is. It's using echolocation. And so that's how it works. And I just wanted to show you that's how the data were collected there. So I need to do this. I've turned it on and I want to come up here and I'm going to do this. I'm going to share my desktop and all goes according to plan. Let me get rid of this. Okay, and so hopefully what you guys should see there would be 2 copies of the Vernier Graphical Analysis Pro here. In fact, let me do this. I want to start a new one here. Let's make sure that one, I tell you what. Okay, so I'm going to come here and do the sensor data collection. And I've got the sensor on. And there's the motion detector, so I'm going to connect to it. And it has a variety of channels. I'm just going to stick with the position channel just so that you can see this. And I tell you what, I'll go ahead and do a second graph. And so the second graph would be the velocity graph here. And now what I want to do is do the data sharing function. And so I'm going to go up here and actually I need to do this. I'm going to stop sharing and I'm going to go up and I'm going to do it again. Let me start a new session here. And so what's happening is that you see a code there. And this code is what you can enter in on your device if you're running Graphical Analysis Pro to receive the data. And so if you really want to be able to do this, I'm going to copy it and I will stick it in the chat here if you need to be able to do that, and I'll enter that. And then I'm going to come over to the phone. And so if I'm sharing the screen there, I'm going to go to data sharing on the phone. And you'll notice there that it says that I need to be able to enter in the code. So I'm going to type in that code on the phone here. And 6HK, connect. Aha, there we go. And so now if you'll notice that I have the position and velocity graph on the computer and I have it on the phone. So the phone is connected, it's via the internet. It actually is, it was a peer-to-peer connection that was established. It went out to Oregon and came back. And so it's now established that way. And so what I want to do is I'm going to come up here and I'm going to hit the space bar and now hit the, oh, there we go. Maybe I'm not. Let me see. Oop. It's fair. But this data right here would be a pretty good toss. And I could analyze that if we wanted to. Now, so I just wanted to be able to do that to show you how that worked. Now, for this particular lab, what we've done is that experiment 16 ball toss is that the data is available already. So what we've done is instead of you having to collect the data for the students to analyze is that you can open the file. And so that's what I'm going to do. So I'm actually going to open the file that we have with the data. And I'll say I don't want to save that one. And I'm going to come here and open up experiment 16 ball toss. Now, the interesting part is you'll notice that on my phone, it's saying, hey, there's a new session. Do you want to join it? I'll even say join. See if it'll do it. There we go. And so I'm sharing now the data file. And so you can share a saved file to it. Now, that being said, I'm going to, let's see here. I'm going to get rid of the phone. I don't want to make it too big there. So, so at this point, this is the data that is from the graphical analysis file that's available. And we're doing the energy of a toss ball. And so the idea is that they need to be able to calculate the kinetic energy. They need to calculate the potential energy. And then they need to be able to figure out the total energy to see whether or not energy is conserved. So the very first part of the lab has them come in, and it actually asks them, I've got the little data table here. I'll just hold it up there. So it has a data table, and it asks them to find various points along the graph where they could get the kinetic energy, potential energy, and total energy. And so obviously this is the part of the graph where the action is. And so I'm going to do this. I'm actually going to highlight from 1 to 2 seconds, and I'll zoom in on that. And then likewise, I will do this on the lower graph so that I'm actually getting the part of the data where the action's happening. And so the very first part of the lab has them come in and mark. So this would be the point where the ball has just left their hands. And so, you know, you've got that there. And so that would be the initial point. Then it wants them to go maybe part of the way up. They find the peak, and they have to find the those values based upon the data they get from here. So like if they're doing the potential energy, you know, they can get the height above that from the data there and calculate it. And they need to know the mass. And it turns out that if you click on there, it actually tells you what the mass is. So the mass, it was 202 grams for the balls that they used for this data set. And so that you would need to know that to calculate those values. So they go through, they find the velocity and do all that, so they can calculate that. Now, what I want to do is the second part, which is a little bit more tricky, is where you actually have to go through and do what's called calculated columns. And in calculated columns, you're going to have it calculate the kinetic energy and the potential energy, and then be able to do a graph of total energy also. And so I wanted to show you how to do that piece of it. So to do this, I'm going to go up to the upper right corner here. And if I go under view options, I want to, so we've got the, let's see, I want the data table here. And so let me do this. I'm going to move this out of the way for me. So we've got the data table. And I need to start off by calculating the kinetic energy of the ball. So I'm going to click on the 3 little dots next to where it says velocity. Anytime you see the 3 little dots, this says, hey, there's something else going on there. And I want to do a calculated column. And in this one, it is going to be kinetic energy. So I'm just going to abbreviate it as KE, and the units are joules. And then it says insert expression. And in the lab, if you've looked at what the lab, it tells you what the expression should be. And so we need to come in here, and we want to, you know, we want 1/2 mv squared to be able to do that. So the way it's done here is that we end up using this expression, and the A term ends up being that 1/2 of the mass. And so they're going to enter that in, and then of course, X will end up being the velocity, and then B is the square term. So I'm going to come here And so I've actually already done the math on there. Let's see, what did I did? So so it's 1/2 of, so that's 0.101 kilograms, and do it in kilograms there. And then we want to make that be 2. And so I can apply that. And so now I have a column here that says kinetic energy. Now, suppose that what I want to do is I want to do another one. I want to do the potential energy. So I'm going to come up here, and I can do it on any of the columns. It doesn't really matter, but I'll do it from position. It seems to make more sense to do it that way. But and so I'll just call this potential energy, PE, in joules. And I need to insert this expression. And so for this one, you know, I need MGH. And so what we have to be able to do is to come in here, and it turns out that we use this equation. So we've got A times X, and so X would be the variable. In this case, it will be the height. B is 0. It's not a term there. And then A is that mass times G. And so again, they have to, and the lab explains to do that there. So let me come here. And so I want that parameter. That ends up being 1.98. So again, it's the mass of the ball times gravity. And then I want to, that one is 0. And I'll apply that. And so that gives me the potential energy column there. So I've created these columns, but I don't have them on the graph. And this is the important part. So I want to come up here, and for the position graph, what I would like to do is make it be the potential energy graph. So all I did was click on the label of the axis there, and I'm going to turn off position, and I'm going to turn on potential energy. And so if I click there, the interesting part is that it looks just like the you know, the position graph, because it's directly proportional to the position there. So it looks like that. Now for the lower graph, I want to come down here, and I want it to be the kinetic energy there. So I'm going to come here and do the kinetic energy. So let me turn off the velocity there. And so now I have the potential energy and the kinetic energy displayed there. So the question is, you know, they've gone through before, and they're supposed to calculate the total energy. Well, we could have another calculated column where we add the potential energy and the kinetic energy together, and then we can graph that if we want to. So I'm going to come here and click on one of those columns there, and I'm going to do add calculated column again, and it'll be total energy with the units of joules. And now I've got to insert the expression, and the expression that we want this time is the, let's see here, I got where did I put it there? Oh, here it's this one. Okay, so it'll be A times X plus B times Y. And so basically what we'll do is we can make X be the potential energy, Y be the kinetic energy, and the A and B terms are just 1. So all we're saying is we want to add those two energies together so that we get the total energy. So let's do that. So we'll come here, and so that's 1. We've got velocity plus the parameter 1 there, and I don't want it to be time. I want it to be the potential energy, and then I'll apply that. And so now I have a column here that has the total energy listed there. And what I would like to do is I would like to see a third graph that has the potential. Well, I want the potential, I want the kinetic, and I want that total energy to be graphed there so that so you can see it. So to do that, upper right corner there, the view options, I could go and do a third graph. And so if I do a third graph, I don't want it to be acceleration. I want it to be total energy. Now, So I tell you what, I might get rid of that first. What if at this point, we ask the students, you've got these two graphs there. What does the total energy graph look like? So maybe you ask them to draw a prediction at this point. We could have had them draw predictions earlier, but there are analysis tools here. And so if I go down to the graph tools, I could do add prediction. And so maybe they come in here and you ask them, well, what's the total energy look like? And they say, let's assume they actually kind of get it. And they come here and they say, oh, well, if you add those two things together, maybe they come up something like this and just kind of get the generalized shape. And if you like it, you can hit save, and there we have it. So that is a tool there. Now, what I want to do is let me come here and actually put that total energy graph there. And we'll overlay that one. And let's see here. Oh, did I mess up my total energy?
So I think you use velocity instead of.
Oh, see? Okay, good. Maybe I meant to do that. So Tom noticed that I use velocity. So what I'm going to do, let me go back here to the total energy. And if I go to column options, I can come here and see, so I use velocity. So I messed up accidentally, but it's good that I did, because you can go back and say, well, it was not the velocity. What I wanted to do was to have the kinetic energy column there, and then apply that. And then if I maybe zoom in on that, we see that actually it did look like what my prediction was. So again, to be able to look at the equations that you've put in there, you just go to the column options and you can see what the equation is for how that was done there. And so you could do that for the kinetic energy column and the others there. So that's how that's done there. So let's see here. Other things that we might want to show them there, Tom, or are you ready to take over and kind of continue on with this?
Yeah, I guess I would just point out that, what you showed in the very beginning about data sharing, if they have GA Pro, they could, data share at this point with calculated columns, or kind of scaffold your students however you needed to along this route. I don't know, do you want to try data sharing to see if anybody out there wants to give it a shot?
Well, we've got it. The session is open. And in fact, it's that same, and in fact, it says 2 clients are connected. So I'm one of those clients because my cell phone is still connected. And then the other one, let me make sure, let's see, because if I do that and let me go back and mirror my screen again. It's doing it, maybe it may not let me do, oh, there we go. Let's see here, let me do that one. There we go. So if I go back and so are you seeing both my cell phone and the other at this point?
Yeah.
Okay, I wasn't sure if I was sharing the app or the screen. So anyway, so you see that even though I did the calculated columns and all that, it also shows up on the phone. And so any work that you did here would show up over there, except for if I come here and the students do examine the data here and do all of that, it doesn't appear on the phone because all I've done is send the data to the other device. So if the student would use the data and analyze it themselves in that. So
Dave, we have a question in the Q&A about teacher says some of my students have borrowed devices from the school, but they have limited access and can't install programs, or have iPads that can't add apps. Does this make it impossible for them to work on graphs on their own unless they use an app on their own personal device?
Yeah, they're going to need to be able to install it. And so that might be a situation where if they're using a device that was provided by the school, you may have to get the school to, say, okay, this is a legitimate app that you can put on there. Because usually that's the way it works. I mean, if they've got a school iPad, there are apps on there that have been approved by IT and all that to have it on there. And the cost is right. It's regular GA. If you want to be able to even just have them open the files and everything like I did, and not even do data sharing, that's free. And so they can install that. If they can't, then they can't be able to analyze that data that we're sharing. The idea is that we've got the software there, you can load it, you can get the data file and be able to do that. So they would need to be able to have that, to be able to interact that way. Now, you could be doing it where, if you're doing a Zoom or a Teams meeting and you're showing what you're doing, they can see it, but they're not getting the data where they can interact with it. So ideally, they would be getting the data to interact with it.
You could, I suppose, export the CSV file, so it might be helpful to show them some.
Yes, good call there, Tom. So what he's saying is, if you come up to the upper left corner, one of the options, of course, you can save it as a graphical analysis profile. The other is an export option. And so one of them is to save it as a CSV, comma separated values. And of course, they can open that with, Google Sheets or Excel. And a lot of people, that's their preference. They'll use the app to actually collect the data, but then maybe they take it out because they want them to use Excel to be able to do it. So it allows you to do that. The graph image basically saves an image that they could print, so you can do that. And then this saves it as a graphical analysis instead of a graphical analysis profile. There's a couple of different things here, but that's how you can take it out and be able to use it with other things there. So.
Yeah, I have to imagine that even
Okay, Tom.
Providing a graph image, students could, if it was large enough and sent to them where they could blow it up, they could pull data off of it to go through some of the experimental evaluation and analysis.
Yeah, and if you've got the data table, let's see, because I think you can actually have it. It will send the data table also. There's a way to do that. So, well, Tom, why don't I stop sharing and let you get to your part of this? So
okay.
Stop there.
So I'm going to be taking a look at energy transformations of a simple harmonic motion lab. This is lab 17 in our Physics with Vernier book. I think that's the right number. The lab is part of the remote data sets that David showed you that he used for his experiment. And so you can get to it there. I am going to show you a slightly different approach, just to highlight another tool that's available through Graphical Analysis Pro. So imagine you're a student for a moment and you're at home and riveted to your screen watching you, the teacher, provide some background on an experiment that they're going to look at. And let me just share my screen here so we can take a look at what that looks like. Go there. I think that'll work. And hold up. I can control my mouse. There we are. We have a video. A little hard to see, but there's a mass on a spring and a meter stick. There's a ring stand. And down here at the bottom, we have a motion detector, just like Dave showed us before. It's a nice little boxy critter here. And so we can just run the video, show that we lift the mass up, we let it bounce back and forth. I will mention that since we're streaming this through Zoom, it looks a little, maybe a little jerky, not quite as smooth as you might hope. When you open this up, and I'll show you in a second, when you open this up in Graphical Analysis Pro, it's really a very nice, smooth video. So the question that we start with when we're talking about energy transformations uh, in this mass on a spring system is just to have the students think about, okay, what would a position versus time graph look like as that mass is bouncing up and down on the screen. And you might have them open up graphical analysis on their computers or their phones or iPads, whatever they have available, and draw a prediction of what that looks like. So I can just kind of demonstrate that. Save, I just want to have maybe just a manual entry screen. And then I can come down here again and say add prediction. And maybe they're familiar enough with this because you've already explored simple harmonic motion that they say, well, it's, it's going to start at some height and it's going to come down and then it's going to come up again. And it's going to look something like that. Maybe they're better artists than I am so that it actually looks sinusoidal, but at any rate, they can provide that prediction. They can share that with you or at least have it for themselves to take a look at. I can save that or cancel either way. And then we'll go back and I'll show you the file that I'm opening up to actually show this, this video. So I don't want to save that. I'm going to go to not any of these options, sensor data collection, data sharing, or manual entry, but in Graphical Analysis Pro, we've embedded experimental data. That's kind of a step beyond what is in our experimental data library that we showed you earlier. So here I can filter by what subject I'm teaching, physics, and I can scroll down through this list. I'm looking for lab 17 and notice that there are 3 experiment files for lab 17. We'll just take a look at this first one to begin with. And that opens up a file that actually has position and velocity versus time graph and that same video. So I'm gonna turn off one of those graphs, just look at position versus time. And now the students can take a look at the graph and compare that to their prediction as to what this was going to look like. We can also, because we have this video is actually the video of this data being collected, we can show those running synchronously. So this set of tools up here, this is a replay tool. Just click on that. We have previously synced up our data set with the video, but I can just run this experiment and you can see there we get the mass in motion, and at some point we'll start collecting data. There we have our data coming in, and you can analyze that, take a look at that, see how that's working. If it's going too fast, maybe you want to slow that down a little bit. I'll make it to 3/10 of the original speed, and I'll just set that in motion again. It's obviously going to take a little bit longer than the 11 seconds that the first one took, but we can just watch that and see how the synchronization of the data and the video line up a little bit better. Have some discussions about looking at that. Data is going to come in any second now. There it comes. There we see it. And we should see that, as the mass is going up, the position is increasing. And as the mass is coming down, it's coming back down in a relatively sinusoidal fashion there. So the lab would have students at this point reflect on, what a velocity versus time graph would look like, and then reflect on the when is the potential energy due to the relative to the spring at its greatest, and when is the relative energy due to kinetic energy at its greatest, and just have actually go through the process of constructing graphs for all four of those scenarios, for position and velocity versus time, for potential energy of a spring, and the kinetic energy versus time, and just provide their own predictions about how this plays out with energy transformations. The next part of the lab really kind of digs into springs and determining the spring constant of the spring, so that we can look at the actual energy transformation from the spring to kinetic energy and vice versa. So that's kind of the first step of this, is just that reflection for this. We can come up here. I need to close this replay tool for the moment and open up the next experiment. Okay, I won't save that. Look at my experiments again. Again, I can filter by book or by subject. Come back up here to click to remove that filter tool. And we want to come here to simple harmonic motion part 2. And you see we get again, a video and a position versus weight graph. This ties into the second part of the lab, which basically has them construct a force versus position graph for the spring. And what we've done here is we've set up a mass whose the length of that mass is always going to be the same, because we're just going to put additional masses on it. And if we watch this video play, we can see that, there we go. The video just allows you to capture data. You can look at the meter stick, or you can just pull the values off of the video, and the data set is already populated into the graphical analysis graph there. So we have a range of 50 to 300 grams. We've noted what the distances are, but notice the distances are the distance measured from the motion detector to the bottom of that mass. And that's shrinking, but that's equivalent to the distance that the spring is actually stretched. So we're really looking at the inverse of this line. But we'll go ahead and grab the linear fit for this particular curve. And we can capture this number right here, the 0.06318 as the slope of that line. And if we think about that, that's going to be in meters per Newton. And we want our spring constant in newtons per meter. So in the lab write-up, they have you actually just go through the exercise of flipping that around. So let me share a different document here. I just kind of captured the very limited data table for this particular experiment. The slope of the position versus force graph, list that, take the inverse and absolute value of that, and you get 15.8 newtons per meter as your spring constant. So now we have the information we need to go to the third part of the lab. The third part of the lab is going to use the same setup. We're going to use a 200 gram mass. We're going to set it in motion, and we're going to analyze the position and velocities as that moves up and down, and look at the energy transformations now that we know the spring constant, and we'll know the mass of the object as well. So that's part 2 of the lab. We can go into new experiment. Again, I don't need to save that. I have my data stored. I'll go ahead and look in the experiment files again. Again, choose physics. And then scroll down here to the 3rd lab in simple harmonic motion, part 3. And in this one, we have, again, the same setup, same video, a position and velocity graph. We can watch the video play, quick 8-second video. We can also go up here. I'll just reset this here. I'll go back and want to take a look at this data collection that we're collecting this time around. Okay, I might want to slow that down a bit. So I'll just go 0.4, just so we can see that happen a little bit more clearly. Get a couple of cycles in there before we collect 2 seconds of data. And there we go with the position and velocity graphs. Now, this is the first time that they can really see these side by side. You could put them in the same graph if you wanted to take a look at those kind of side by side, how they match up. So you can see that, okay, my velocity is at a minimum here, but I have to be careful about this. Yeah, the taller graph is my position. So when my velocity is at 0 at the top and the bottom of the run, and my velocity is at a minimum going downward as we're just coming out of that downward space there. Okay, so let me get back to this graph here. The lab would next have us create calculated columns, very similar to what David did in the last experiment. You'll notice something fairly unique about this. The lab calls for us to 0 the position sensor for this portion of the lab. So we 0 it when the spring is at equilibrium. So the mass is just hanging there. That's our 0 point. And you get that oscillation around that, that position that we've created as an origin. And the lab itself just kind of says, you know, if we do this, we can just pay attention to the potential energy of the spring. At the same time, we're paying attention to the kinetic energy of the system, and not worry about the potential energy due to gravity. We leave that as an extension for the students to explore why that's a reasonable thing to do, but don't cloud the investigation of this transformation of energy with that information at this point. Okay, so I can close that for now. I can go once again to, I can turn these off and on at will. So I'll just close all of this and open up the data table. We're working with data set 2. I could do this in either location, as David mentioned before. If I create a calculated column right next to the position, out of the position column, it's going to assume that I want to associate something with that position. So for this, I'm going to look at the potential energy of the spring. It's going to have units of joules, and my expression is going to be 1/2 K, the spring constant, times that displacement squared. And so I'm going to use this equation here. I'm going to use 1/2 of my spring constant, which in my data table, let me see if I can find that real quick. I noted to be 15.8 newtons per meter. So I can put in 15.8, but I want half of that, so that's going to be 7.9 times position, or the stretch of the spring, if you will, squared, not to the 6th power, but squared. And then I can hit apply. And now I have potential energy for my spring in joules. Notice that it calculated it over here as well. And then in my velocity graph here, I can do the same thing for kinetic energy, add a calculated column. Again, I'll just say that's KE and joules. And we're going to look at 1/2 times the mass squared. And my mass for this one was given as 200 grams. So that's 0.2 kilograms times the velocity raised to the 2nd power. And we can apply that. I'll mention something about data set 1 here in a second, but let's go back and look at our graphs for a moment. And if we just look at a single graph, I'll get rid of the data table so we can really focus on this. And instead of position, let me bring in my potential energy and my kinetic energy. And we can take a look at this and recognize that as one is going up, the other is going down, and that's kind of as we might expect. This would be a point of comparison, so students would be able to look at their predictions and try to understand how they either understood or didn't understand what was going to be happening. Maybe recognizing that all of our energies are going to be positive in this case because we're dealing with squares of velocity and squares of distances. So now I can come back into my data table and I can create that total energy graph as well. And let's do that here. Add a calculated column. And TE. Now, there was something about that graph that was making me a little suspicious, but I'll have to go back and take a look at that here in a second. We want this same A times X plus B times Y to get those two added together. And again, kinetic energy and not time, but potential energy due to the spring, that elastic potential energy. And then we have now a total energy column. And if I go in here, doing this with some trepidation, click on total energy, and that's oscillating. So that tells me I did something funny in my calculations here. And I wonder if anybody has caught what my error was.
Yeah, it's in the chat. Somebody did.
It's
Pam
in the chat.
caught it.
So help me out here, Ann. What did I do wrong?
You didn't do the half term. You did the mass term.
Oh, so let's go back into column options. So 1/2, we're looking at the K.
Yeah, it was for the mass when you did doing the kinetic energy. When you're doing the kinetic energy,
okay.
you
There we go. So again, column options. These are just great learning moments. I always told my students in class that every mistake I made was for their benefit. So let's try that.
And Pam caught it, so you know,
ooh, yeah.
She's paying attention.
Yeah. So this is still not the prettiest graph. You might say, your students might look at this and think, this is not happy data, or this is not telling me anything about the is energy conserved. But this is where our auto scaling feature trips us up a little bit here. So I'm going to go into my graph tools and look at graph options and just set my scale for my y-axis a little bit more friendly. I'll go actually to 0.1 and click outside of that. And then you can see that, well, in the big scheme of things, that is relatively constant. You could even come in here, look at statistics and pull off the mean value of that total energy. You could also look at, this is a system that may have some drag associated with it, and you may arguably be able to say that there's a decrease in energy here. So you might want to take a look at a curve fit and just apply a linear fit and take a look at that. A slightly negative slope. So yeah, you're losing some energy over time if you wanted to look into that a little bit further. Okay, so that's the the analysis that they do is to look at the energy transformations, make some observations about is energy conserved in this case or not, and just another opportunity to explore that energy transformation. Were there any questions that popped up in the chat at this point?
There's a question about the data share. Would you let me go back and share graphical analysis? That may be better because I've been looking at the question. I wanted to clarify that. So let me go here and let's see, we've got graphical analysis open here. So let me share graphical analysis. And so I'm going to do this and I'll just say new experiment. So the question came up about the software manual saying, oh, you need to be on the same network. I'll start my video here too. That you need to be on the same network. Now, what that's referring to is under data sharing. If you look there, it says connect to a LabQuest, Logger Pro, or graphical analysis source. This graphical analysis source is what's different between GA Pro and regular graphical analysis. When it talks about using it with the LabQuest, it does have to be on the same local area network or the same network. It can be even done over a VPN, but it has to be on the same network. What's different now is that the data sharing that's this way, maybe I'll stop sharing that and go back, is that it's a network connection, but it is an internet connection. And this is key because it turns out the LabQuest, they can generate their own Wi-Fi network, and it's possible to have the LabQuest send data from the LabQuest to another device running graphical analysis via this Wi-Fi connection, but the Wi-Fi doesn't have to be on the internet. For data sharing and Graphical Analysis Pro, it has to be the internet. I did it where one day I was on my phone using the cellular data, and because what's happening is that you're connecting through a server in our office that establishes this handshake between the graphical analysis on one device and the other device. And so that is an internet connection. So it's not the same Wi-Fi local area network. It is the difference. And somebody brought up what the manual says. I don't think the software manual has caught up yet to the software. Because this data sharing function has only been in there for about 2 weeks. And so I think that the manual hasn't caught up. We're trying to show you the feature of almost before the manual comes out there. So that's what's happening there. And I imagine that will be clarified in the manual pretty soon, but I think the last time I checked, it was not there. So I don't know, Tom, if you wanted to add anything else to that.
have to unmute myself, of course.
Oh, there you
No, I actually was distracted by another question that came up in the chat. So
Oh, okay. Okay.
I hammered
Um,
away at a little
yeah, so
question about that.
that's the difference. And, you know, it is a little confusing in that it's the same name, but it's doing it differently. And in fact, I actually did this one day. I took my, I had a lab quest and I was data sharing locally from the lab quest to my computer running Graphical Analysis Pro. Then I established the data sharing with it sending out data from here, and I was sending it to another colleague who was in Oregon, and so she was receiving the data that I was collecting here in Tennessee on my lab quest on her graphical analysis. So that it's possible to do that, but it's two kinds of data sharing that are there. So hopefully that helps answer that question.
Yeah, we have another question about if you're using Graphical Analysis Pro, do the students need Graphical Analysis Pro as well? Can you touch base on how that works?
Yeah, so the way it's done, it's Graphical Analysis Pro is a paid app. And so right now you can get it at $69 for a site license for your school, which means that what happens is, let's say you pay for it and you get access for the remainder of the year. And then basically it's going to be on a yearly basis, is that you will get a code that you send to the students, and that allows them to turn the graphical analysis, the free app becomes the paid app. And so it's really inexpensive because basically you pay that one thing and then all your students have access to it. Now, we saw that in the option here, it is possible when you save or when you export that you can export it as a .ambl file. That is a regular graphical analysis file. So there are ways you could share it. You know, if you saved it this way and emailed it to them, you can always send them a file that way, or drop it into a chat or something like that. The difference is that the data sharing is that live interaction, and that's the nice part, because they see the data as you collect it. And you can have the students interact with it, but that's how it's done. And of course, right now for this one, I think we put in a short-term key. There is a 30-day free trial, and so if you haven't signed up for that one, we would recommend that you could do that. There was also that 30-day free trial for the Vernier video analysis app that we mentioned, but I know we are almost out of time. And so it allows you to use the video to do analysis. And it turns out that, I did the ball toss. I could have done that in the video analysis. Could have done it via video and actually analyze the motion straight from the video without any sensors. And that's the power of that app, is that you can measure motion without having any sensors at all. You're just using a camera to be able to do that. So. Does that pretty much, is there any other questions there?
There was a little discussion in the chat about friction in that last activity, and looking at, the fact that the spring going up and down is going to have that internal friction from the metal itself being stressed and unstressed, as well as air resistance. And it could be an interesting exploration to have the kids investigate that, think about how they might quantify it in some way or another.
Or maybe this is a perfect example. Maybe you're teaching virtually, and you do have access to something that you can set in motion like that. If you could put it into a vacuum somehow, where you could see where you reduce the air friction to see what happens. But that could be something where you're interacting with them and say, well, what happens if you do this? And then you do this. Maybe they make a prediction based on that change in what you're doing there. So we think that whole ability to do that, the data sharing, is perfect for where we are right now with the virtual schooling. So.
Well, I see we are right at 12:30. It looks like we've answered questions that are outstanding. So we thank you for showing up today and participating in this webinar. I hope you've gained a little bit for your unique teaching situations this year. Please know that we're here for you. If you have questions, if you want to explore a new experiment or get to know these tools a little bit better, you can call us up, you can email us, you can use the chat on our website, and we'll reach out and help you as best we can. Any last words, Dave?
No, you summed it up there. So, don't be afraid to give us a shout, and we're here to help. I will say that this Graphical Analysis Pro, I mentioned that this new feature, the video, was added recently, the graph and the data sharing. There are other features. It is going to be growing fairly rapidly with some new features as we go on, and we kind of sped up the development of this. We were wanting to do this anyway. And it was like, okay, now we really need to do this because that makes it most appropriate for being able to do it in a virtual environment. So,
again, thanks for taking time to be with us today, and appreciate the work you're doing out there. Take care.
And there'll be more. So,
There's more.
other ones coming for physics and chemistry and biology. So.